Hello, myself Namita from Information Science and Engineering Department, studying at Sri Venkateswara College of Engineering. So the topic of today's video is deterministic finite automation and non-deterministic finite automation. From the subject Automata Theory and Compiler Design 21 CS51. Let's get into the contents of the video. The contents are Introduction to DFA and NFA, its definition, properties, difference between them, regular languages, regular expressions, NFA to DFA conversion, DFA minimization, their applications, limitations, compiler optimization, DFA versus NFA performance, its practice, and finally the conclusion. Introduction to DFA and NFA. DFA and NFA are two types of finite automata used in automata theory and compiler design. DFA stands for Deterministic Finite Automation and NFA stands for Non-Deterministic Finite Automation. Both DFA and NFA are mathematical models used to describe and analyze the behavior of systems. Definition of DFA. A DFA is a phi tuple where Q is a finite set of states, sigma is a finite set of input symbols, that is alphabet, delta is the transition function mapping a state and an input symbol to a few state, Q0 is the initial state and F is the final state. DFA processes input strings by transitioning from one state to another based on the current state and the input symbol. Properties of DFA. DFA is deterministic, meaning that for each state and input symbol, there is exactly one transition. DFA has a unique path for every input string, leading to unique final state. DFA is closed under complementation, intersection, and union operations. Definition of NFA. Same as DFA, it has phi tuples and the meanings are also same. NFA processes input strings by transitioning from one set of states to another based on the current set of states and input symbol. Properties of NFA. NFA is a non-deterministic, meaning that for each state and input symbol, there can be multiple transitions. NFA can have epsilon transitions, allowing it to move to a new state without consuming any input symbol. NFA can have multiple paths for a single input string, leading to potentially multiple final states. Differences between DFA and NFA. DFA has a unique transition for each input symbol, while NFA can have multiple transitions. DFA does not have epsilon transitions, while NFA can have them. DFA has a unique path for each input string, while NFA can have multiple paths. Regular languages and DFA. DFA is closely related to regular languages, which are a class of formal languages describable by regular expressions. DFA can be used to recognize and accept regular languages. Regular languages can be represented by DFA, with each state representing a different language pattern. Regular expressions and NFA. NFA is closely related to regular expressions, which are a concise way of representing regular languages. NFA can be used to recognize and accept regular expressions. Regular expressions can be converted to NFA with each state representing a different expression component. NFA to DFA conversion. NFA can be converted to an equivalent DFA using the subset construction algorithm. The subset construction algorithm generates a DFA with states representing sets of NFA states. The resulting DFA has a unique transition for each input symbol, making it deterministic. DFA minimization. DFA minimization is the process of reducing the number of states in a DFA while preserving its language. The minimization algorithm merges equivalent states to create a smaller DFA. Minimized DFAs are easier to analyze and implement. Applications of DFA and NFA in compiler design. DFA is commonly used in lexical analysis, that is scanning, phase of compilers. DFA can efficiently recognize and tokenize input strings based on patterns defined by regular expressions. NFA is used in constructing the non-deterministic finite automation for regular expression matching. Limitations of DFA and NFA. DFA and NFA are limited to recognizing regular languages only. They cannot handle more complex languages such as context-free or context-sensitive languages. More powerful models like pushdown, automata, and Turing machines are used for such languages. DFA and NFA is in compiler optimization. DFA and NFA techniques can be applied to optimize regular expressions matching in compilers. Techniques like state merging and table compression can reduce memory footprint and improve performance. Compiler optimizations can transform NFA-like expressions into more efficient DFA-like structures. DFA versus NFA performance. DFA has better performance than NFA in terms of time and space efficiency. DFA has a fixed number of states leading to predictable memory requirements. NFA can have exponential memory requirements due to the non-deterministic nature. DFA and NFA in practice. DFA and NFA concepts are used extensively in real-world applications like lexical analyzers, regular expression engines, and pattern matching algorithms. Compilers and text processing tools heavily rely on DFA and NFA techniques. Understanding DFA and NFA is essential for efficient implementation of these tools. Conclusion: DFA and NFA are fundamental concepts in automata theory and compiler design. DFA is deterministic and has unique paths for input strings, while NFA is non-deterministic and can have multiple paths. DFA is used for recognizing regular languages efficiently, while NFA is used for regular expression matching. Thank you.